Hi folks, welcome back to this lecture about exploring data, and in part 2 we're going to look at a really important different element to a data set that we need to summarise, describe using descriptive statistics. That is variability. We've talked about central tendency, I want to talk about variability, and in order to do that we're going to look to some extent at this topic of visualising the data, because by visualising it we can actually kind of conceptualise the variability as well as the central tendency. And eventually that will bring us on to discuss confidence intervals and error bars in the final section of this talk. So a really nice way to visualize the degree of variation in a data set is to plot a frequency histogram. So it may not be the first graph you think of plotting when you're trying to explore your data, but actually it's really useful. So here I've plotted the data on hyena scats that we got from the previous example, where if you remember the mean number of scats per latrine was 3, so that's what's indicated on this in the centre of this graph. What we can see on the x-axis is the number of poos or scat, and up the y-axis we've got the frequency. So this graph shows you the kind of shape of the distribution. What we can see is that obviously you can't have negative poos, so the distribution is bounded at 0. And we can see this kind of slightly lopsided tail on the right hand side of the distribution, where we've got just a few latrines which have relatively large numbers of scats, while the bulk of latrines have only 1 or 2. And that was something that we kind of picked up on to some extent when looking at the mode, the median and the mean earlier. But as well as this central tendency represented by the median, the mode and the mean, we have this property of variability, which it would be really useful to be able to describe, because you can imagine that for different data sets it can vary a lot. We could have a situation where hyenas produce latrines which are all very consistent in terms of size, or we can have huge variation. And how do we quantify that? Well, we're going to look at this in the context of an example of a slightly different data set, this time a quantitative data set, as opposed to the previous discrete data, because they were in the form of counts. If you remember, you can't have a fraction of a scat or a negative scat, so those are kind of count data. They were they were discrete, and here we have quantitative data in the form of the swimming speeds of sperm. Okay, so you will realise by now that biologists have some pretty obscure interests, one of which is understanding how sperm swim and some of the factors that affect sperm swimming speed. And you might think that's pretty obscure, but when you start to think about it, as we'll see in a sort of expansion of this example in a later lecture, it turns out to be really important, not least for human fertility. And you might be aware of issues with male fertility on the decline in developed countries, and we're going to have a look at an example of a piece of research on that topic later on. Anyway, for the time being, let's imagine that we've recorded the swimming speed of a whole bunch of sperm in a sample. And that's what the data set consists of, all these numbers here, 2.4, 2.1, 2.6. These are expressed in millimetres per minute, which is, if you think about it, not very fast, but that's how fast sperm go. And actually for something as small as a sperm, that is quite fast. And like in the previous example, we have 20 data points. We've got a sample size n of 20. But this time the data are on a quantitative and in fact continuous scale from, in theory, a speed of 0 up to a speed of infinity, anywhere in between, depending on how accurate our measurement method is. So we can do the same kinds of things as we did with the previous data set. We can calculate the mean swimming speed, which in this case is 2.3 millimetres per minute, and we can visualise this in a frequency histogram. In order to plot a frequency histogram of continuous data like this, we need to divide up the x-axis into actually arbitrary bins. Because the data are on a truly continuous axis, we could divide this up in many different ways, whereas with the hyena scat, you've either got 0 scat, or you've got 1, or you've got 2, so there's a kind of natural way of dividing the data on the x-axis. But for a frequency histogram with a continuous variable, you have to make a sort of user decision about how to divide it up. And in this case, I've gone for intervals of 0.1 millimetres per minute. And when you divide the data up like that, you can see it looks sort of a little bit like the previous example, but this time maybe a bit less lopsided. It's a relatively small sample size, only 20, and as a result this distribution is not very smooth. If we got more data, then we'd expect this distribution to smooth out. And unlike the previous example, the mean swimming speed falls right in the middle of the distribution in sort of coincidence with the modal bin as well. So this distribution is rather more symmetrical than the previous one, but nevertheless, like the previous one, it shows a lot of spread. So we've got variation in the sperm swimming speed. You can have sperm, the slowest sperm down here, swimming at about half the speed of the fastest sperm. And that's variation that we might like to quantify, this variability. So how do we quantify variability? Well, the standard method is to think about each individual data point and compare it to the mean or some other measure of central tendency. So typically it'll be the mean. So in this case, we know that the average sperm swims at 2.3 millimeters per minute. And in order to understand the variability, what we're going to do is compare each individual sperm to that average. If the data set is very consistent with very low variability, then all of the sperm are going to have swimming speeds which are very close to the mean. If, on the other hand, this is a really variable data set, then we're going to expect to see lots of big differences between each individual swimming speed measurement and the mean. So the logical thing that we need to do here is to calculate that difference between the data point and the mean, which is known as a deviate. So we take the mean away from the data point or vice versa, and we get a difference, and that difference is known as a deviate. So just a couple of examples. In red here, we've got a sperm that's swimming quite fast, 2.4 millimeters per minute, faster than average. There's a difference of 0.1 from the average. And in purple, here's a slow sperm that's swimming 0.6 millimeters per minute slower than the average. So the deviate is minus 0.6. And you can instantly see here that the deviates have sort of two bits of information embedded in them. One is, well, the size of the deviate, the magnitude of the deviate, tells you how far away the data point is from the mean. And the sign, whether it's negative or positive, tells you whether the data point is bigger or smaller than the mean. And that's going to turn out to be important in a moment, because we can go through the whole data set and we can calculate the deviates, and that tells us something about the variability in the data set. But it's hard to make sense of all of those deviates like that. What we need is some kind of indication of what the average deviate looks like. And to do that, the logical thing to do is, first of all, add up the total amount of deviation in the data set, which gives rise to something called the sum of squares. So if we add all the deviates up, that would be the logical thing to do to quantify the total amount of variation in the data set. But of course, all of those negative deviates are going to cancel out the positive ones, and we're going to end up with a sum of more or less zero, because of course about half of the data points are going to be above the mean and half below the mean, so they'll cancel each other out. So that's why we do a trick, which is to square the deviates before we add them up. So the sum of squares is, remember, this Greek sigma means the sum of the differences between the mean and the data point squared. So we take each difference and we square it, and then we add it up. So I here indicates the fact that we've got multiple data points. So for each value of I between 1 and n, we have a deviate because we have a different data point to compare with the mean. And each time we square it before we add it, so we get the sum of squares, which really is a sort of quantification of the total amount of variation in the data set. But of course, that sum of squares is going to get bigger the more data we've got. So it's not really a sort of fair measure of variability because it's affected by the sample size. So the fact that the sum of squares in this case is 3.24 is not very meaningful. It's a number that's just going to get bigger and bigger the more data we have, which isn't, that even though the data set isn't necessarily getting more variable just because we've got more data. So a common thing we're going to want to do is to essentially average these squared deviates, so divide them through by the sample size, which is exactly what we do to calculate something called the variance. So the variance, which is typically denoted s squared, is the sum of squares, the sum of all the squared deviates, divided by the sample size with a little correction tweak of -1 in there. It's the reason we do the -1 tweak is a bit weird, not something you need to worry about at this point. Focus on the concept here. The concept here is we're trying to work out the total amount of variability and then divide it by the sample size in order that we know how much variability is there per data point. And that's then going to give us a fair measure of the variance of the data set. So in this case, it's 0.171. And at that point you might think, job done, we've got a number that we can use to compare different data sets. But hang on a minute, 0.171 is not in very meaningful units. The reason why it's not in meaningful units is because we took the nice data that were in millimeters per minute and then we squared them. And that's messed things up because now they're in kind of millimeters per minute squared, which is not something that really makes any sense in the biological universe. So the very common thing that we would do next is to square root that variance to create something called S, which is commonly known as the standard deviation. You've probably heard of it. So the standard deviation is the sort of genuine average amount of deviation per data point expressed in units which make sense in terms of the original data. So in this case it's 0.413 millimeters per minute, and what that is the average amount of variation between a data point and the mean. So on average, if I pick a data point at random, I'm going to expect it to be about 0.4 millimeters per minute different from the mean. So the bigger the standard deviation, the more variable the data set. If it's close to zero, every data point in the data set is going to be more or less the same. Okay, so that's the end of that little section. The final section of the talk after the break will be a little bit more about visualizing data, and then we're going to get stuck into, first of all, confidence intervals and error bars, and also distributions.